Hello, my name is Ana Maria Briciu, and today I'm going to talk about enhancing the performance of software authorship attribution using deep autoencoders. This is a brief outline of the presentation. I'll tell you a little bit about the authorship attribution task and what that means in the software domain. And after that, I will tell you what we propose in terms of software authorship attribution. And of course, at the end, I will present some conclusions. These are the two articles that present in detail the approaches I'm going to show you today. And we get to the maybe more interesting part about what authorship attribution actually is. As you may guess, it's about identifying the likely author of a given text. And I think we all can think about applications in the real world, in literature. So the first attempts to identify the author were on literary texts. But of course, in terms of plagiarism, we can go in the field of education and so on. Maybe less obvious is what authorship attribution means in the software engineering domain. So software authorship attribution, well, it's pretty much the same. We still want to identify the author of a code fragment. We still want to identify the author. But now we talk about the code fragment. And why this would be relevant? Because it can help, such systems can help in processes of software quality, in plagiarism detection, of course, similarly like the classic authorship attribution task. So for example, we could use a system of software authorship attribution to maximize the benefit of the code review process. We take a code fragment and we know who is supposed to be authored by, but the system tells us that maybe it's not that person. So what does that signal to us? That maybe either it was not indeed authored by that person, or maybe it was authored by that person, but it's below the standards of coding that that person usually provides because of time constraints or other constraints and so on. So it can offer some intuitions in other software engineering processes. Of course, there are some challenges as well to software authorship attribution. So for example, we know there's a lot of code reuse in real teams of developers. A project is worked on by multiple people. And of course, we have, if we consider simple characteristics like structural and layout characteristics, well, in a lot of times, these are altered by code formatters. All right. This was what authorship attribution means. We try to develop flexible, adaptable models of authorship attribution. We actually started from an authorship attribution model designed for literary texts. And we thought, well, could the same model work on code? And the literary authorship attribution model was also based on autoencoders, but we believed it was general and we decided to test it on code as well. But we still maintain some inspiration from the natural language processing domain, and we drew on that knowledge to try to propose novel methods for authorship attribution of software. In terms of what already exists, there are bits and pieces that already existed when we proposed our models. So researchers have used natural language processing inspired features in code related tasks. And even autoencoders, as you can see in the last bullet point, were used, for example, for authorship verification and some other classification tasks. However, altogether, they weren't, so it didn't, the model as a whole, with all the bits and pieces, it didn't exist in the literature. So to actually tell you about what we did, we developed two autoencoder-based models, one called AutoSoft, which targeted multi-class software authorship attribution, and the other one, SoftID, which also dealt with software authorship attribution, just in a one-class configuration. First of all, because I told you that both our models are based on autoencoders, I should tell you what autoencoders are. Well, they are deep learning models which are used in medical data analysis, image analysis, and a lot of other fields. They actually try to reconstruct the input they are given. So we call them self-supervised learning techniques. And they have two parts: the encoder, which tries to obtain a meaningful latent representation called the code, and the decoder, which from this particular latent representation tries to reconstruct the input it was given. The intuition is that once the autoencoder is trained, it will reconstruct well data from the same distribution, so similar data to what it was trained on, and it will badly reconstruct other data, which is the idea we based our models on. First of all, the formalization of the software authorship attribution problem, how we view it. Okay. We view it as a classification problem, a multi-class one, in which we had a set of developers, a set of software programs for said group of developers. And what we wanted to do was develop a model that can tell us, given a software program, who it belongs to from the given set of developers. This is an overview of the model. We started with the data collection. I will tell you in a minute about the data set we used. We took the data, the texts, the code, the source codes, and put them through a lexical analyzer, and we obtained the tokenized text. The feature used for the autoencoders are doc2vec features. So this is where the natural language processing part comes in. And these embeddings were split into train, validation, and test sets and given to the autoencoders. We trained n autoencoders, so one for each developer. And based on the similarity of the testing instance and the reconstruction of the autoencoder for that particular instance, we decided to which author that particular instance belongs to. I'll go into a little bit more detail in a few minutes. Okay, so I said that I would go into detail about the data set. The data set is the Google Code Jam data set. Google Code Jam is a programming competition, and it makes for a good data set for authorship attribution. As we know, or it's mostly probable that each file is authored by a single person. We chose the 87 most proficient developers from the whole Google Code Jam dataset, and we also took smaller subsets to see how our model performs in different settings. So the 87 developers were the ones that had more than 100 files in the set, and so on. The 5 developers had, the set of 5 developers were those who who had more than 200 files, and so on. And here we have the results. So as you can see, we obtained pretty good results for all subsets, but as expected, the performance decreases once we increase the number of developers. Intuitively, we expected this as, of course, it's harder to distinguish between 87 developers. What we also did was vary the n-gram size. N-gram meaning we have groups of a sequence of tokens can be, a line of code can be tokenized into single tokens, meaning a variable, an operator, or so on, or we can take groups of tokens. And we found that even though taking groups of tokens into consideration performs better in all cases, then simply taking the tokens, we couldn't find universally beneficial n, where n is the size of this group of tokens. Okay. We also compared, of course, the performance of our model with existing classifiers. So we took some traditional machine learning classifiers and compared the performance of our model. As you can see, it compares pretty well with most of the classifiers considered. Only the support vector machine classifier outperforming Autosoft. But as opposed to the support vector machine classifier, I will skip this slide because I talked through I made the same points during the earlier slides. So as opposed to the support vector classifier, Autosoft is a little bit more adaptable. So without changing too much, we were able to actually extend the model. So propose an extension of the model, which was intended to be a prior stage to the multi-class classification. We wanted to decide the likelihood that a software program doesn't belong to any of the considered developers. So in a similar way, we saw, we wondered if it's a given test instance, if for a given test instance, we obtain very distant reconstructions for all autoencoders, maybe we should classify it as unknown. It probably doesn't belong to any of the developers considered in the original set. And here are some results for this extension. As you can see, we tested again with unigrams, so simple tokens, and 5 grams, groups of 5 tokens. And while unigrams perform well in some cases, it's using 5 grams, it's a clear improvement. So these groups of words much better capture the style. Okay. I did not include this table. It was a very big table in the presentation, but we also compared these results with a one-class support vector machine classifier. And Autosoft actually compared favorably. Where one-class support vector machines worked better was in terms of specificity. So that is a point of, we mark as a point of improvement in later experiments. The second model, I told you I will tell you about 2 models, is SoftID, which is also based on autoencoders. The main difference is how we formalized the software authorship attribution problem. We still have a set of K developers, but this time we train an autoencoder on the whole set of programs belonging to them. And when we are given a new software program, we try to see if that program is written by one of the developers in the original set, or it is not. Much in the same way, like for AutoSoft, we computed a distance between the testing instance and its reconstruction by the autoencoder, which we trained. This is a cosine distance, but it can be anything that expresses the similarity between two numerical vectors. And we computed the probability, and based on this distance, and if it was greater than the threshold, we marked the instance as belonging to an author that is not in the original set of developers on whose programs the autoencoder given was trained on. Else, if it was below this threshold, we marked it as original. Original meaning belonging to the initial set of developers. We continued to work on the Google CodeGem dataset. This time we took subsets of 3, 5, and 12 developers. And for the other class, for instances that do not belong to this considered developers, we took them randomly from the rest of the data set. And here are some results. I forgot to mention, we use, here we use representation, TF-IDF representations and latent semantic indexing. So still drawing from natural language. And we, again, with we experimented with a number of n-gram sizes and to see if we can find a trend one way or the other. We actually couldn't again. What we found was that the latent semantic indexing representation works a little bit better when we have more authors. But other than that, it has remained unclear if there is a universally beneficial n-gram value. It's more the combination that generates the combination of testing configurations and n-gram value that gives us an idea of what happens. Again, we compared this our model soft ID with one class support vector machine classifier, and as you can see, we obtained in a lot of the cases, about 95% to be exact, better results. So the positive values are marked as the improvement, as mean the improvement of soft ID, and negative values such as this one mean an improvement provided by the one class support vector machine. As you can see, it's overwhelmingly positive values, sometimes very biased by a very large margin as well. So most of this I said, so the here is better phrase that the ideal n-gram value depends on the testing context, and maybe a point I haven't made yet is that a tool like soft ID may be important or can be important in the software development process if we think about small teams. like a bit between 3 and 12, like we have in our testing configurations. Overall conclusions tell us that the 2 autoencoder-based models proposed provided relatively good results on both of the formalizations of the software authorship attribution tasks. And what we considered a good advantage is that our models are general and we can adapt them to suit different needs as it is required. Of course, we want to carry out experiments on data sets collected from real software development teams, as some researchers point out that the data set we use can be a little bit artificial, as in, for example, in real software development teams, there's a collaborative effort to develop programs. Here, we know for sure that people worked on their on a single file at a time, and they all solve the same problem. So we want to see, our next step would be to see how our models fare in the, well, so to say, in the real world. And beyond the references, that would be it from me.